All right, hello everyone. This is going to be part 2 of the Unit 5 kinetics notes. We're going to start off by talking about integrated rate laws. So integrated rate laws are basically rate laws for different order reactions that have been integrated using calculus. Do not ask me how, because I haven't done calculus in about 10 years and couldn't hope to explain the actual steps it took to get there. But these rate laws are going to be utilized to show concentration changes over time or predict concentrations at a particular time interval, or even calculate how long it's going to take to get to a certain concentration. So we can see the 0 order, the first order, and the second order rate laws here, right? So to take a look here, this is the 0 order rate law rearranged from what you saw on the previous page into y equals mx plus b format. So into the straight line format. Now, you'll notice that a sub t is y, m is represented by negative k, x is represented by t, and then that a sub 0 is going to be our b. So what this means is that negative rate constant, that negative k, is actually our slope. Now below this, you're going to see 3 graphs. We have this one here on the left that looks like a straight line with a negative slope. We have this one in the middle, which is a curving downward line, and this one on the right, which actually looks like an exponential growth to me. So when you are looking at any particular graph, you can tell which order that particular reaction is that graph represents by looking at what the shape of the graph is and what your axes are. So most of these graphs are going to have time on your x-axis in seconds or minutes or whatever it happens to be. But on the left here, you could have a couple of different options. So we're seeing on the left one, we have just our basic concentration of whatever reactant. In the middle, we have our natural log of whatever concentration of reactant, and we have 1 over that reactant on the right. If you see a random graph like this, you are looking for the one that is a straight line, because again, y equals mx plus b format is in fact a straight line. So if you notice that there is a straight line in the graph where the y-axis is just the concentration of A, then it is a 0 order reaction. If you were to see the straight line on the graph that has your y-axis as natural log of A, you would be looking at a first order reaction. And if the straight line exists on a graph where the y-axis is 1 over A, then you would have a second order reaction. So basically what I'm telling you is this example here on the left is our 0 order reaction graph. Okay, so moving on to first order, we're again seeing that equation rearranged into y equals mx plus b format, y equals mx plus b. But this time, you're seeing that straight line on the middle graph, the one that has natural log of A. Again, if you see a straight line and you notice that the y-axis is natural log of A, you are looking at a first order reaction. And then finally, moving on to our second order, y equals mx plus b format, same situation, y equals mx plus b. Now we are seeing a straight line on the graph on the right, the one that is 1 over our concentration of A. There's one other difference here as well, and that is that our slope is in fact positive on our straight line, where you were seeing a negative slope on the other two. So those are all factors and indicators that you could use on an AP question to determine what the order is of a particular reaction if you're just looking at a graph. Okay, so here we have a sample problem. We have this really, really big reactant over here, plus this little ion yielding some products. Initially, this thing is blue, and when those two react, the products will be colorless. And our little blurb says blue food coloring can be oxidized by household bleach to form colorless products as represented by the equation above. A student used a spectrophotometer set at 635 nanometers to study the absorbance of food coloring over time during the bleaching process. In the study, the bleach containing this ion is essentially at a constant concentration throughout the reaction because it is in dramatic excess. The student used data from the graphs below, and I know it says below, but I actually moved them above because that made more sense. And it's asking you, based on the graphs, what is the order of the reaction above? So right away, I'm looking for a straight line. And if you look at the data on the graph on the left, you'll notice that is not at all a straight line. That's a curve. The graph on the right, a curve. But the graph in the middle is pretty much just perfectly a straight line. And you'll notice that the y-axis is the natural log of that absorbance value. So when we see a straight line on the natural log y-axis graph, we know that this is a first order reaction. If we had seen the straight line on the graph on the right over there, it would have been second order. If it had been on the leftmost one, it would have been a zero order. So that's what you're looking for to answer that question. Next, we have another sample problem, and that sample problem says NO2 is produced as a byproduct of the combustion of fossil fuels in internal combustion engines. At elevated temperatures, NO2 decomposes according to the following equation, seen right here. The concentration of a sample of NO2 is monitored as it decomposes and recorded on the graphs, again below, but realistically up here. The two graphs that follow it are derived from the original data. Explain how the graphs indicate that the reaction is a second order reaction. Well, once again, I'm asking you to look at your data and look at what the data is telling you. This over here, if we were to draw a best fit line, looks like a curving line. This graph down here definitely looks like a curving line, but this one is a straight line. Relatively. So we notice that our y-axis is 1 over our concentration of NO2. In our example graphs a few slides back, we know that when we see our straight line with a positive slope in 1 over our concentration of NO2 on our y-axis, we know that that is a second order reaction. So that straight line there tells you that information. So that's your indicator that explains how it is a second order reaction. All right, another sample problem. We can use rate laws to determine concentrations of reactants, how long it takes for a certain amount of reactant to disappear, or how long it takes a certain amount of product to form. So our question says for the reaction, 2HI yields iodine gas and hydrogen gas. Our rate law looks like, whoops, too far. Our rate law looks like the thing you're seeing on the right, K times the concentration of HI to the power of 2. If this is 2.4 times 10 to the negative 21st and 0.0100 moles of HI is placed in a 1 liter container, how long will it take for 10% of that HI to react? Okay, so the first thing we have to do is figure out what rate law we are supposed to be using. So it says that the rate law for this reaction specifically is over here. So we're going to use this to figure out which integrated rate law we need to be using. And we know that we can tell what order the reaction is by adding together all of the orders of the individual reactants. In this case, there's only one reactant, and that happens to be second order. So 2 plus nothing else is still 2. So overall, this reaction is going to be second order. Because of that, we are going to use the second order integrated rate law, which I'm just going to write down on the left over here. 1 over our concentration of A sub T, which is going to be our final concentration, is equal to K, which is our constant, times time, plus 1 over our initial concentration of A. All right, so that is the integrated rate law that we will be using to solve this problem. So let's look at what we're given. We are given K. That's this number right here. So we know what number that is. And we know that 0.0100 moles of HI is placed into a 1 liter container. So we do, in fact, have an initial concentration because 0.0100 moles divided by 1 liter is 0.0100 molarity. So we know this number, our initial concentration. And what we are being asked is how long it will take for 10% of our HI to react. So we have to actually figure out our final concentration. But we have an initial and we know how much of it has reacted. So that's an easy enough thing to figure out. After 10% of that HI reacts, 90% of it is left over. So if we take 90% of our initial concentration, 90% of 0.01, we are going to get 0.009 molarity, because that's 90% of our initial concentration. So by doing that, I just figured out what my final concentration is, and the only other variable, the one I want, is T. So we just go ahead and fill in all of our numbers. So 1 over our final concentration, that 0.009, is equal to K, again, this number, 2.4 times 10 to the negative 21st times T, plus 1 over our initial concentration, which was again given to us, 0.01. All right, and when everything is said and done, I should be rounding my answer off to 2 significant figures because this number gives us 2 sig figs. Everything else has more than that. So all I have to do is solve for T, rearrange my equation and do that. And when everything is said and done, I get 4.6 times 10 to the 21st seconds. The problem does not ask for that information in any particular unit, so seconds is fine. You could rearrange it into minutes or hours or whatever you wanted to do, but it doesn't ask for that, so why bother? Next thing I want to talk about is half-life. A reaction half-life is the amount of time that it takes for the concentration of the reactants to reach half of the initial amount. So if you've heard of half-life before, you've probably heard of it in terms of isotopes, which is one popular way that we talk about and use half-life. But we can talk about half-life in terms of pretty much any reaction we want to. So there are 3 equations here for different order reactions and half-life. So half-life of a 0 order reaction is equal to the concentration, the initial concentration of A divided by 2 times your constant. For a first order reaction, it's equal to the natural log of 2 divided by your constant. And for a second order, the half-life is equal to 1 divided by K times your initial concentration of whatever reactant. So these are more or less plug and chug equations that you can just go ahead and plug things into. So let's look at this first sample problem. So this problem says, consider a particular isotope of iodine that is radioactive. If the half-life is 13.1 hours, what is the rate constant? So the first thing to know about radioactive decay is that it is a first order process. So this would be something to know if you happen to be taking the AP exam. Radioactive decay is considered a first order process. So you're going to be using that first order equation, which happens to be T 1/2 is equal to ln of 2 divided by your constant. So realistically, this equation is pretty simple, actually. So all you have to do is fill in what you have. We are given the half-life, which is 13.1 hours. So I'm going to bring that down, 13.1. is equal to the natural log of 2 divided by k. If you rearrange your problem and you solve for k, you will get your answer right away. Plugging that into a calculator, I get that k is equal to 0.0529. Now, in terms of units, if you go back and you look at the units for k in a first order reaction, you will see that the unit should be seconds to the negative first. Now, it's seconds to the negative first because seconds is generally the time unit that we are usually dealing with in reactions. However, if your time unit is different, then your unit for k has to change accordingly. So because we are dealing in hours, it's actually going to be hours to the negative first instead of seconds. But as before, usually it is going to be seconds to the negative first, your units for k. But just because we are dealing with hours this time, that does actually have to change as well. All right, next sample problem. The radioactivity of a sample of iodine 131 was measured. The data collected is represented by the graphs below to the side. The decay of iodine 131 is a first order reaction. Again, radioactive decay is generally a first order reaction. So there's a few different things to do here. A, determine the half-life of iodine 131 using the graphs. Label the vertical axis of the second graph. Identify the correct units for the rate constant K for the decay reaction, and explain how the half-life of iodine 131 can be calculated using the slope of the line plotted on the graph. Okay, so a lot of stuff is happening here. So let's tackle it one at a time. Letter A, determine the half-life using the graph. So if we look at our graph over here, our initial concentration, or initial rate, I should say, is way up here at 16,000. A half-life occurs when that drops down to half. So half of 16,000 is 8,000. And we see that point happening right over here. So it took 8 days for that rate to drop to half. Okay. So let's double check. Let's see if that happens again. Half of 8,000 is 4,000, and we see that happening at 16 days. So again, it's taking 8 days to drop down by half again. So our half-life is 8 days. Our second task is to label our vertical axis of the second graph. So this is a straight line. And because A, the problem tells us that it's a first order reaction, and B, radioactivity is a first order reaction, we know that that straight line is going to occur for natural log of your concentration. So our labeling of that axis would be natural log of concentration of whatever it happens to be. In this case, it's going to be our concentration of that isotope, but depending on what it was, that A might be something different. Okay, so that's A and that's B. C asks you to identify the correct units of the rate constant K. C asks to identify the correct units of the rate constant K for the decay reaction. So once again, when you look at that chart that I gave you for the proper units of K for different orders of reactions, you're going to see seconds to the negative first next to first order. However, we are not looking at time in seconds here. We are in fact looking at time in days. So instead of seconds to the negative first, you're going to see days to the negative first as our unit for K in that first order reaction. Finally, explain how the half-life of iodine 131 can be calculated using the slope of the line plotted on the graph. So if we are calculating the half-life, we know that the slope of that line in a first order reaction is going to be equivalent to negative K, because that's what this graph is telling you. This graph is telling you it's a first order reaction because you're seeing that straight line at that point. So what we can do here with this graph is we can use any particular data point here, plug it into the first order integrated rate law and solve for our constant, and then plug that constant into the half-life equation to get our half-life. All right. Next, we have another sample problem. This asks, the reaction above is a first order reaction. The rate's on constant K for the decay of the radioactive isotope X, according to the equation above, is 2.3 times 10 to the negative second days to the negative first. The slope of which of the following graphs is correct for the decay and could be used to confirm the value of K. So this is it's throwing a lot at you, but basically we have a couple of key things here. We know it's a first order reaction. It's a radioactive isotope. Radioactive decay is first order. This is our constant for K. It's asking the slope of which graph would be correct for that decay. So looking at this, we should be seeing a straight line graph that matches a first order reaction. So if you go back and you look at the first order reaction straight line graph, we should find that straight line in a graph that has a y-axis of natural log, right? So automatically A is out, it has the wrong y-axis. Automatically B is out, it has the wrong y-axis. Automatically D is out, it has the wrong y-axis, and automatically E is out, it has the wrong y-axis. So with that piece of information only, you can identify the correct answer. Okay. Another thing to pay attention to is that slope positive or is it negative? The only place that you saw a positive slope would be a second order reaction. And since this problem tells you that it's a first order reaction, B doesn't work and D doesn't work. So using that information, you can whittle down to your correct answer. All right, that is it for part 2. Hopefully this was helpful. If you have questions, please ask me either in class or in ELT.